Hey everyone, welcome back. This video will be all about a German mathematician and astronomer named Johannes Kepler. So Kepler came up with three laws of planetary motion as you see outlined here. All right. Kepler was one of the biggest and most influential, I'll say, minds of the scientific revolution when it came to astronomy. Right. The first one really was, I guess you could say, Copernicus. Right. He was the first one to propose that, hey, the Earth is not the center of the universe. It's actually the sun. Right. He wasn't quite able to show that, right, to prove that. But a little bit later, Kepler here studied Copernicus's work, and he studied under another guy named Tycho Brahe, who was a Danish astronomer of the time. And Kepler used Brahe's observational data of the orbit of Mars around the sun. Brahe, or Tycho as he's named, had an incredible eyesight. So he could track and record the movements night after night of these celestial objects, specifically planets. And so Kepler used Brahe's observational data of Mars to, well, record the movement of Mars over time, specifically over a year, right? In fact, over several years. And he did this so much that he was able to come up with three laws of planetary motion just based off of observational evidence. Okay, he wasn't actually able to use a telescope to observe the planets and their motions. Okay, he just did it based upon the numbers and observations from Tycho. A little while later, after Kepler, came Galileo, and he tweaked the telescope and was able to further observe and prove Kepler's work. So let's start off with Kepler's first law of planetary motion. He said that orbits are elliptical with the sun at one focus. So I should say that Kepler only focused, if you will, on planets around the sun. Okay? So let's take a look at this. Kepler said, so law number one, Kepler said that all planets move in what's known as an ellipse. And this is a very exaggerated planetary orbit. Most planets in our solar system are pretty close to circular, but I'm just doing this for demonstration purposes. So, an ellipse is pretty much the scientific term for an oval, right? If you were to squish a circle, it would become an ellipse, and the focus or the foci points are right here. And so the more elliptical, the closer these foci or focus points for singular would get to the edge. Okay? A circle, by the way, has both foci at the center. So the more elliptical it gets, like this, right, these foci points get closer to the edge. The more circular it gets, the closer these foci get to the center. Okay, so that being said, we have this being the major axis and this being the minor axis. Okay, half of that being the semi-major and half of the minor being the semi-minor. Okay, and these are traditionally given variables as a and b, so I'll kind of just write, let's do that, a and, b right there. And so, by the way, this is one focus, and an ellipse has two foci. Okay, so for planets around the sun would be located at one of the focus points, right? There is, in theory, right, in space, just hanging out, another focus point on the other side. Okay, but the center of mass of the sun is just, at one of them. And so that means that the planets would be going around in this path around the edge, right? So say this is a planet out here of mass lowercase m, and it's, traveling around, arcing in this ellipse, around and around and around. Okay, so this is his first law. All what he called satellites move in an elliptical shape with the sun at one focus point. Okay. Law number 2 deals with the motion in that ellipse. Okay, so actually let me copy and paste this onto the next slide. Will it work? Haha, love that. All right, so now, taking into account that the planet here, right, is moving around this ellipse, there is always some tangential velocity, right, which means that there's also some velocity towards the sun, right, for some total or net equivalent velocity, right, at some angle. So actually, let me draw it a better way here so you can better visualize. His second law is quite a phenomenal law when you think about it, right? When you realize what it actually says, what it actually means, it's really fantastic. So what they say, or what it says, is that the planet, for instance, now that I'm deleting almost all of it, I didn't need to copy, I guess. So, okay, when the planet is at this position and the time it takes to go over to this position, so let's call those points A and B, right? It sweeps out some area right there, right? Some area we'll call, A1, right? And it takes some time to do that. That's the same area as when the planet goes from approximately point C to point D. So that's the same area as something like this. All right, and we can also call that, well, area, but let's call that A2 instead. So this says that area 1 is the same as area 2. But let's look at the differences, right? It's the same area, but the distance traveled between A and B is much greater than the distance traveled between C and D, right? Why might that be? Remember, these are planets, or they could just as easily be comets around the sun, right? Any satellite, anything in orbit around another object. In the case of planets, that's the sun right there. So when the planet is at position A and B, it's much, much closer to the sun than it is way out here at C and D. So the gravitational force at these positions is strongest, or rather is stronger than it is over here. If the force is stronger, guess what? It's going to be accelerating at a greater rate, right? It's going to be changing speeds at a greater rate. And in fact, I don't know if I quite drew this to scale, but this position here, it'll be traveling the fastest, right? So this should be the closest it'll ever get to the sun, right? And in the case of the sun, this is called the perigee, closest to the sun. Okay, or I'm sorry, perihelion. There we go. Perihelion. At that position right there. So thus the force of gravity is strongest right here, thus it'll be traveling the fastest. And distance equals rate times time, and there you go. This point over here is the furthest from the sun an object will ever be. So that position is called aphelion. Right there. okay? And so thus out here, the force of gravity is the weakest. And so it'll be changing speeds the least amount and thus traveling the slowest, all right? But equal areas in equal times mean these are the same. So what effectively is happening is that, let's say it starts at A. It speeds up over here, slows down. Well, let me do it again. Slows down. It's going the slowest right there. And then once it passes it, it starts to speed up. Speed up. Right? Try this again. Speed up. The fastest, and then slows down. Right? Actually, let me do the dot. So like this. Speed up. Slow down. Speed up. Slow down. Right there. Something like that. Right? For planets around our sun, because our orbits are pretty much circular, the difference in speeds in 1 year is barely perceptible. It's there, but it's barely perceptible on a macroscopic scale, right? We can't perceive it. The people that are in charge of the times, right, the calendars, NIST, they can tell for sure. Comets definitely changes speeds, right? Comets, their orbital shapes are very elliptical. Okay, so this is in essence Kepler's second law: equal areas, equal times. For the third law, right? For law 2, we can put that into an equation form, and in fact, your book goes through this. It's the angular momentum, right, of the satellite or of the planet at any point divided by twice its mass. And the thing is that this value here is constant. It doesn't change. But the dA dt, that's equal to that constant. Okay, so that's another way to write that. If you wanted to see how this comes about, it should be in your book. Okay, I won't do it here. All right, the third law is that the period of orbit squared is proportional to the semi-major axis. Remember, the semi-major axis was half of the major axis, right here. So let's see where that comes from. Okay, I'm going to do it though for an idealized case. So let's say the sun is right there, mass m, and we have a planet moving around it. And let's do it for a pretty circular orbit. Okay, it has a tangential speed like that, and then a distance from the planet of capital R. And that, for the most part, stays constant, okay? So the net force on this planet of mass lowercase m points inward, right? The net force is ma, but the actual force itself is the gravitational force, right? So we can write this as the gravitational force equals ma, right? Which is the net force. However, because this is a circle, what kind of a acceleration is this? It's a centripetal acceleration, right? So that means it's also written as mv squared over the radius of the circle, which is capital R. And so knowing what the force of gravity is equal to now, gmm over r squared, that's equal to mv squared over r. The masses go away. One factor of r goes away, right? And we're getting down there, right? We can solve for this speed. V equals, what is that? G times the mass of that central object, in this case the sun, divided by r, and square root. And this is known as the orbital speed, okay? Because in this case, in theory, if it's a circular orbit, this orbital speed remains constant. Because if it's a circle, r won't change, and the mass of the central object probably won't change. And so this v orb stays constant, okay? Now, let's take this a step further and relate it to the period, right? How long it takes to go one time around, in other words, right? You know that as 1 year, basically, but let's put that in SI units, right? So in terms of uniform circular motion, the period we can write as 2 pi r over the speed. And this is coming from distance equals rate times time. So solving for time gives us distance, which is the circumference of this circle, divided by the rate, which is that v orb. So now plugging this in gives us 2 pi r over gm r. I have to keep the square root because it's just v orb, not v squared orb. And now I'm going to put this in the form of t squared. Okay? So I'm going to square both sides. That means I have t squared, and then I have 4 pi squared times r squared divided by gm over r. Right? Flipping and multiplying gives us 4 pi r cubed over gm. Right? And this form right here, this t squared equals 4 pi r cubed over gm. This is what's known as Newton's form of Kepler's third law. Okay, right here. Newton realized, because he came up with what the gravitational force was equal to, right, or rather the form of it, he did this analysis here and realized that, hey, Kepler, you're right. Right? Your theory is correct. The period squared is proportional to the semi-major axis cubed. In this case, for a circular orbit, right, you don't use A, use R. Right? If it was an ellipse, you would just put A in there. Right? Another thing to realize is that all of this right there, that's constant. That's constant. And so this is why we can say that the period squared is simply proportional to r cubed, right? And this is for a circular orbit. If it was for an elliptical orbit, we would say t squared is proportional to a cubed. Okay, so this here is the big takeaway from the third law. Okay, the time it takes to go around is directly proportional to the semi-major axis. Okay, and those are Kepler's 3 laws of planetary motion. Thanks for watching.